All right, so let's start. So today we are happy to have Andrei Okounkov from the University of from Columbia University. The title is on the screen: Monodromy, Yesterday, Today, and Tomorrow. Andrei, go ahead.
Yeah, thanks. It's great to see some old friends. It's also great to meet many people I've hadn't met before. This talk will have several parts to it, and first is completely elementary. It's in fact some based on some talk I gave previously, so it's a completely general audience talk. And so I guess I don't think I can read. Sorry, I can't comment on what's going on in the chat. So this is I think we'll go very quickly through that, since I'm not familiar with the bulk of the seminar participants. So my thinking is that we're going to go pretty quickly through some general material and then talk about some more advanced things. But if you need to be slowed down, let me know. So what's monodromy? It's kind of a really basic concept. If I have a linear differential equation, of course, and we will be interested in linear differential equation with rational coefficients, of course, I can solve it along any path, as long as the path avoids the singularities of my solution. So maybe this is the red crosses indicate the singularities. And so if I let's see okay. Let's okay, well, cool. So if a path comes back to itself, then the solution will not necessarily come back to the same solution. And so if I take like a fundamental solution of a linear differential equation, some matrix, evaluate it, if I solve it along a path, and then evaluate it at the and evaluate the ratio of the fundamental solution at the beginning and the end of the path, we'll get some matrix which would be, by definition, very clearly, by construction, very clearly representation of the fundamental group of, well, I had the equation, so I had the equation with rational coefficients, so some was defined with, say, projective, and if it's in one variable, it will be in projective line without the singularities equation. So I get the representation of the fundamental group of that by matrices, and that's called the monodromy. And this is the concept which I guess was introduced by Riemann, except of course he meant completely opposite from he meant monodromy. Mono comes from word one. He meant really the absence of monodromy. That was supposed to be the monodromy. And then of course there's when I gave this talk before, a joke was made, and this should be called manodromy or something like this. But so not from the word many, not from the word mono. But anyway, that's the concept. And then now, for instance, so if I have an equation of the form is indicated here, maybe the other way to write it is I take z d by dz, and then I take a constant matrix. So that's another way to write the same equation. So the solution is solution is, this is what we teach our students in elementary differential equation course how to solve this equation. The solution will be whatever this coefficient matrix say naught times log z, and the whole thing exponentiated. And so in particular, if I go around the origin, I pick up 2 pi I, exponential of 2 pi I, this matrix A naught. And so we see that this is monodromy is a map, in this case, from Lie algebra, which is, so I had a connection with some, if I have like a constant coefficient connection, or z by dz connection, that matrix I should maybe think about as an element of Lie algebra. And then I get exponential, which is a map from Lie algebra to Lie group, and monodromy, it's a clearly generalization of that concept. And so, okay, going to the next slide, is of course more generally, you don't have to You don't have to study equation in one variable. You can have a flat connection on some bundle over some base manifold, and again, you're gonna get and then this means you had a Quatermain connection on a bundle means you have a first order differential operators that tells you how to move in every direction. And then if you look, this will similarly, if you have a path that avoids the singularity, you're going to have a monodromy. And so you're going to get a representation of the fundamental group of your manifold, take away the singularity, and you have to choose a base point. And that will be representation by automorphisms of your bundle at that point, a fiber of that bundle at that point B. So this is my favorite quote about monodromy. So maybe we can just take a minute. You can read it. So Nick Katz had well, first of all, Nick a large chunk of Nick's work has to do with exploration of various monodromy type effects and primarily number theoretic situation. And he's a big somehow they did a lot to popularize the power of this concept. In fact, had a website called monodromy.com, which is now defunct, but it is available on the Wayback Machine, and so you can go and read this. And there's much more there. It's a fun website to read. And so that's anyway. And so in general, we're not being concerned with these properties of this map is because this is an interesting map. It goes from flat connections to representation fundamental group, and this is falls in the general category of questions covered by kind of the general realm of the Hilbert's 21st problem. We're more interested in computing monodromy of specific equations. So interesting. I'm not sure where that came from. Let me erase it. Not sure. I have some funny mark on my screen. Okay, well, anyway, somehow appeared there. Anyway, I don't think it's disturbing the presentation. So this monodromy falls into a general category of maps when you have like a transcendental map between algebraic varieties. So for instance, and this is the case to consider. So suppose I have a quotient of an algebraic variety by discrete group. So that is very often another algebraic variety, but the map, the quotient by discrete group, is not an algebraic map. And so, like for instance, exponential is a quotient by translations, and similarly, you can take upper half plane quotient by SL2Z and other things like this. And so then you can ask, then you have a map between transcendental map between algebraic varieties, and then you can ask, you can focus on things that are algebraic in both complex, kind of both algebraic structures. Those are very special ones. Like for instance, like if I take exponential of 2 pi I rational number, I get the root of unity. And if I take a J invariant, if I in my upper half plane I look at J invariants not of an arbitrary elliptic curve but a complex multiplication elliptic curve, I'm going to get an algebraic integer and so on and so forth. So we would be interested in the situation when we have an equation. The equation has something is defined over some equation is defined with some nice coefficients, in particular maybe some nicely rational functions of some bunch of variables, and the monodromy is defined over exactly kind of the same type of coefficient, namely rational functions of maybe exponential of all these variables. So things like that. So we're interested in monodromy specific equations. We're not, and usually, like I said, and usually it's a map. And so usually, if I give you a random equation, monodromy exists but cannot be really written because it's not, it's some analytic object. It's not an algebraic object. And conversely, if you can give you monodromy, and that corresponds to some equation which cannot be written in some closed form because it's, like I said, it's not, its coefficients don't belong to some field that you can somehow that you can get your hands on. So And also, of course, we will be interested not in the. I wonder why is this? Is that what's that line? What's that red line? It's not sure what the origin of that red line is.
Don't worry
not
about
on
that.
Yeah.
That is one of the participants probably using pad or something. Just draw it.
Oh, okay.
Don't worry about that.
It's like an annotation. Okay, that's just, yeah. Well, yeah. Anyway, so also we're interested in the equations. Although we're interested in linear differential equations, we're not interested in like the things. So when people studied differential equations, classically, they were interested in actual solution, like what the actual phenomena they represented were solutions to linear equations. Like Airy, he was thinking about, he was an astronomer, and his equation was, and similar, Bessel was an astronomer, so Airy was more like a. Anyway, they were interested in actual wave phenomena, like when they studied their equations, and so whereas we of course study the linear equations at the monodromy, we study not for the actual solutions. Okay, there's some solutions from linear equations, but rather for there are some special functions, the coefficients of which have a certain meaning in representation theory, in enumerative geometry, and whatever in theoretical physics, if I may say so. So it's more, we're interested in solution as packing certain information. Even the coefficient equation itself packs a certain information, which the coefficients have a certain meaning in various branches of mathematics and physics. And so I want to make a reference to, well, if you want to kind of learn more about what I have to say, it's there are many places to do it, but one thing is that we had a fun midrasha in Jerusalem a couple of years ago, and so that would be, lectures from there. It's a kind of fun place to learn more about the kind of the meaning of these equations, but also the other resources, and I'll mention some more resources later. But it's maybe to place you in the general world of kind of literature. The kind of equations we will study are belong to the general sort of kind of Lie theoretic type flavor equation. So that would be an example of that was like a Knizhnik-Zamolodchikov type equations, and so which and as I said already on the previous transparency, in fact, we in the world where we in the world of interstrass, we would be in fact, all these equations have a natural Q-difference generalization. So from the point of view, if you think about like the actual propagation of waves or diffractions or some stuff like that, then okay, maybe Q-difference equation seems like a strange thing to consider, but from our point of view, it's very natural. And so allegorical Q-difference equation, that's just the same as before, except instead of ZD by DZ, you have a shift. So ZD by DZ is like a infinitesimal multiplicative shift by Z. And then we put just a regular multiplicative shift, which for analytic purposes, maybe it's good to assume that Q is not of absolute value 1. So it's either bigger than 1 or less than 1, and let's say it's less than 1. Because if it's bigger than 1, you write the equation the other way, then it's rename the variables and Q becomes less than 1. But so this is a regular Q-difference equation would be something of this kind, and regular means that that the matrix, if a matrix is regular 0, means the matrix A of 0 is regular and invertible. So
and either Stokes phenomenon for Q-difference equations like irregular theory.
Oh, I was gonna say that if you want to learn about irregular singularity for Q-difference equation, then in fact the organizer of the seminar who just spoke is one of the world's experts on this. He wrote, right? Jan, you remember you wrote a kind of an important paper on the subject. So, but this will not appear today. So you can direct your questions to Jan directly. Today today will
yeah,
be
you shut me up. Yeah, okay.
yeah. So we will be content with regular equations. So you can, and so you have a regular singular point, then just like for ordinary differential equation, you have a solution in a neighborhood, a holomorphic solution in the punctured neighborhood of that point, and then which is that just by the equation itself will be extended meromorphically to a if A is that a rational function, then the equation itself gives you meromorphic continuation to the whole complex plane with singularities. Q translates of the singularities of the coefficient of z. And this is the same principle that we teach our students when we talk about meromorphic continuation of a gamma function. Gamma function satisfies a difference equation, and the difference equation gives a meromorphic continuation. And so that's a difference or Q difference. It's for that perspective, it's more or less the same. And so for instance, so maybe but Q difference is easier because many various analytic questions are easier. Like for example, if you want a Q gamma function, then or the reciprocal of the Q gamma function, that's just given by convergent product. So if you want to, so ordinary gamma function is a function with, or maybe reciprocal of the ordinary gamma function is a function with zeros at 0, -1, -2, and so forth. So you can try to represent it by corresponding product, except that product needs to be regularized. And for Q gamma function, you don't have to. It's convergent product, so it's just written here, and it solves the if you shift the variable by Q, it solves this equation, which is just also written here. And then in general, we have a 1-by-1 difference equation, regular. Then it will have a solution of the form which I wrote down here. So it's a product of Q gamma functions and some overall prefactor. And so then you can ask, what's then how you're supposed to think about the monodromy? And there's a definition which goes back all the way to Birkhoff, so it's like 100 years old. So this is, if you want to know, the monodromy will now be instead of going back from starting at some point and coming back to that same point, we instead will be going from, so you have a transformation, z goes to qz, and we will be going from one fixed point of the transformation, which is z equals 0, to another fixed point of the transformation, which is z equals infinity. And we'll just compare, so at each of these points, we have a solution which is holomorphic in the neighborhood of that point and meromorphic in the whole plane. Then we'll take the ratio, and there'll be a function meromorphic in the whole complex plane, and the difference, well, I guess take away 0 and infinity, and then the difference with ordinary monodromy, I mean, this is quite striking. It takes some getting used to, but it's once you think about it for a minute, it becomes clear. Then so to compare and contrast with the usual monodromy, the usual monodromy had depended on a path, but did not depend on the variable, right? The variable in which you take the variable in, maybe I should have said this more clearly. So if I have a monodromy of a differential equation, it's in the equation is in variable z. Then if you take the monodromy, that variable z cancels out. The monodromy, in other words, monodromy is a constant for the differential equation. For differential equation, being a constant means it really is a constant. Constant means that d by dz of that thing is 0. So and for the Q difference equation, it's no longer depends on the path, but it still depends on the variable. In that meaning if you have if you take this monodromy the way I defined it, and you take and you shift it by q, you see this is not going to change. But if you have a function and shift it by q, it doesn't mean, and it's not going to change. It doesn't mean it really is a constant. It just means it's an elliptic function. So this means you have the monodromy is a function on an elliptic curve, which is c star modulo q to the z. And so instead of being a function of a path, it's now a function of the elliptic function of the variable. But in fact, it contains, as we will see, I'll kind of explain on the next picture, it contains as much information as representation of this pi1. And so in a 1-by-1 case, you can since in 1-by-1 case, we wrote down the general solution of a general equation, then if you take the ratio of this such, you'll see that this will be an explicit product of theta functions. Theta function is kind of a monodromy of a model Q-difference equation. So, all right. So this is I'm trying to explain what's going to happen. So suppose now Q will go to 1, and what would be how would we recover the monodromy of a differential equation with a differential limit? So if Q goes to 1, then the equation, my difference equation, my shift becomes infinitesimal, and infinitesimal shift is differentiation, so I'm getting a differential equation. And I'd like to kind of pictorially explain what's going to happen in this limit. Well, if I have some singularity of my equation, then the singularity of the solution, see if I can. Then the singularities of the solution, we can see my pointer here, I think. So the singularities of the solution that's holomorphic near 0, they'll form geometric progressions with denominator q that go off from the singularity to infinity. So there'll be blue things in this picture. Conversely, singularities of the equations that the solution that's holomorphic near infinity, its singularity will be geometric progression starting from the same singularities of the matrix of the coefficients, but now going to 0. And so you get as my q goes to 1, these two chains of singularities will condense into a cut, and so then what I will getting is if I'm interested in the, maybe I'll try to say it pictorially, if I'm interested in the monodromy around this path from 0 to infinity, that I have to make sure that I keep my variable z here, and then I take the limit q to 1, and I see the transport on this path. If I keep my variable z in some other place, and I'll see the transport along some different path. And it's clear that if I know the transport of my equation along all paths that go from 0 to infinity and avoid the singularities, then it's clear that I know the monodromy of the differential equation. So that's why this kind of Q difference or elliptic data contains the same information as representation of pi1. And so the equations we were going to consider are the all kind of various relatives of what's called the quantum differential equation or the Brodin connection. And as I said, already, but I'll repeat it, that this is a linear differential equation. From this sense, it's one of the most classical objects that there is in mathematics. And the word quantum refers to not to the fact that this is this linear differential equation is somehow satisfied in some very strange sense. It refers to the meaning of its coefficients, the coefficients of both the equations and the solutions in enumerative geometry or high energy physics and so on and so forth. So that's what quantum means. So all right. And so maybe I'll give the definition of what's this quantum differential equation. So in its more basic form. So there's a notion of a quantum product, and it's an associative, simply commutative associative deformation of the ordinary cup product in homology of an algebraic variety. And instead of in the structure constant, that is to say, you have three cohomology classes, and you'd like to multiply them and pair with a third class. So this is the constant. This is the structure constant, the quantum differential equation. Instead of being so ordinarily, this would be if I take structure constant of the cup product, that just counts triple intersections of cycles. But now, instead of triple intersection of cycles, I allow them, instead of intersecting a point, I allow a count of rational curves or holomorphic spheres or pseudo-holomorphic spheres that that meet my three cycles, and then and that count I organize with some weight, which is I remember the homology class of that curve. So I think I introduced like a counting variable, which is in a variable in the group algebra of the cone of effective curves, and that's convenient to represent it in the form z to the class of the curve. And then you can think of z as being some variable in some torus, which is the dual space, which would be H2, H upper to tensor the one-dimensional torus. So that's an operation, and it's clear it's defined as some operation on the vector space, which is the way it's written. It's a formal power series in this semigroup of effective curve classes. And so in principle, every operation is some infinite sum. It contains infinite amount of geometric information about all possible curves of various degrees that meet my my three classes. Okay, that's the definition. And of course, this is I should say that this is when people say, well, let's count curves, it really means means a lot of technology has to be set up for this to be done properly. And then, well, I'm not gonna. Of course, I'm not. That's not the place to go. Today is not the time, and this is not. This talk is not the place to go into setting up these technicalities. But that's if you count means you're really integrating over some moduli space and set up this integration correctly. That requires a certain a definite amount of technical work. And very important information about this. Interesting. Okay, here there's some lag between when I change the slides and it's changed on your screens. So very important information is stored by the solution of what's called this quantum differential equation or the Brovin connection. And the equation is written deceptively simple. It says that the derivative of my function in the direction, so it's a function on torus, which is a torus base modeled on H upper 2, and in particular the tangent bundle, like the tangent vector, the constant tangent vector fields to that torus are H upper 2 of x. And so I'd like to, if I want to differentiate my function in direction of some particular homology class in H upper 2, all I do is and what does it mean differentiated? If I have if we look here, so then differentiate means if I differentiate z, if I differentiate monomial z to some power, some class of a curve, then down comes the factor, which is just the pairing of my homology class with the corresponding curve class. And so this the equation says the derivative of this f is that class quantum product with the solution. And so this looks like, in fact, a constant coefficient differential equation. But then you realize that there's my product is some operation that depends on z. So it's a linear operation, but it's not constant coefficient. So it's some linear operator. This matrix is as it stands is in fact a formal power series in z. And then even prove its convergence is a very hard usually a hard problem. Prove that it can be analytically continuous. It's a never harder problem. But there's a class of varieties for which, in fact, it can be generally shown to be, in fact, a rational function. So the fact that I started with equations with rational coefficients, and then I switched to this context, then from this perspective would be a little bit surprising, or should be a little bit surprising, is that we start with counting curves of different degree, and you get this generating function which is rational, which means all this having a rational generating function means having very effectively having a bounded amount of information in curves of all possible degrees. So this means curves of very few. Not only it's a rational function, it's in fact there's some bounds on what denominators can be, and then it says that in fact curves of low degree they contain all possible information about curves of high degree. But that's, I mean, it is a bit of a miracle, and but it does happen for a whole lot of varieties. And so in particular, one class of such varieties, and I don't want to be too dogmatic about it. There are many other varieties, or there may be a more general class of of interesting varieties for which this rationality can be proven with modular technology. Oh. Right. So, but at least this occurrence spectral resolutions, which maybe I'll talk a little bit later, for them it can be proven on general grounds, is that in fact the quantum differential equation, like I said, already the equation itself is equation in principle is born as some formal power series, and the fact that it's in fact a rational function is already some state, and that the fact that the rational function can be understood in some representation-theoretic terms, that is another statement. And then the third statement is that the monodromy of that equation can be also understood in some representation-theoretic terms. It's a third statement. So there's something from the point of view of curve counting that is that's kind of three separate, well, not three separate, three related, but terms which are kind of each of them more and more surprising. But also from the point of view of applications, maybe I should say, make it clear that this is when I say that the current subtractive resolutions are like Lie algebra of the 21st century, I'm not trying to say that you should forget about the Lie algebra of the 20th century. This theory does include the old theory. So in particular, it does give you. So people did study equations like the Knizhnik-Zamolodchikov equation, the Knizhnik-Zamolodchikov equation. It does give you, so studied the monodromy, and for the Knizhnik-Zamolodchikov equation, there's a theorem of Kohno-Drinfeld. For the Knizhnik-Zamolodchikov, there's been some partial results. And the theory I'm going to explain is that it gives a uniform result for all cases covered by this geometric theory. So that's not only it doesn't. I mean, it includes the old problems in representation theory you can do, or the old problems in like Knizhnik-Zamolodchikov, Knizhnik-Zamolodchikov, that has to do with either conformal field theories or some integrable quantum field theories on lattices, and monodromy, integral representation of solution, that plays a very important role there, and the fact that we can do all of that uniformly here. In fact, some of the most general form of the monodromy Knizhnik-Zamolodchikov equation, that wasn't known. That people did work on that, but it wasn't known in the generality that can be done now. So sorry, so I guess I'm saying that there's some kind of analytic point I want to make, some geometric point I want to make, without maybe going into much details, and they're all more interesting, more clearer in the Q-difference situation, and also in enumerative geometry that's much clearer. So the Q-difference equation, it happened when you, instead of enumerative geometry, usually is set up as intersection theory and some moduli spaces on some stuff. So this takes place in homology, if you want, or maybe the Chow ring. But since we're extracting numbers, homology is good enough. But you can upgrade, and you can ask, well, what about taking this counts in K theory? Means in K theory, you instead of if you write down solutions, so you had some moduli problem, such some describe moduli of some kind of object, and then you write equations that supposed to describe the kind of object you'd like to enumerate. So in cohomology, you're just asking for, basically the degree of the cycle determined by these equations, whereas in K theory you can ask for the sheaf defined by these equations, some sheaf. So you can ask for that sheaf, so for its sections or something like that. And so and that usually contains much more information. And in particular, the Q difference equation becomes really, you can kind of geometric, means the Q comes from the Q is the variable Q, which was abstract, is now becomes concrete. It's just an element of automorphism of P1. We're interested in counts of maps from P1, and the shift by Q is just really the automorphism. Like, for example, when we think about like the fundamental solution of the equation itself, is usually a matrix. A matrix means it's some tensor with two entries, and we on the previous slide we had like a three-pointed curve, which was had like a tensor with three entries, but the tensor with two entries looks like a map from P1 with two marked points. And so then Q that leaves one parameter group of automorphism is Q is an element of that group of automorphisms. So and that's and you get the Q difference equation in both the variables that I explained, but also you get the variables in the other variables. And what are the other variables? You can study your modular of maps with respect to the action not only by the automorphisms of the domain, but also of the target. So if you have some automorphisms of the target, they will act on modular of maps, and if you set up the enumerative theory coherently, they'll be all fine. And you get you also get commuting difference equation, those variables. And in fact, those variables, if the action of those variables is self-two, we'll say, for instance, is preserved as a symplectic form, then that in fact be regular difference equation in those variables too. And jumping a little bit ahead, maybe this is a place to mention that there's a certain set of ideas labeled 3D mirror symmetry that includes in particular this symmetry of such enumerative situation that exchanges the role of the variables z that count the degree of the curve to the variable of a that correspond to just action by some group of automorphisms of my target x, and that's very nice because, for example, for instance, the Q difference connection in one and the Q difference connection in the other, they're just really exchanged by that transformation. So maybe I'll try to say it more clearly. You have some variety x, and some it's for our 3D mirror dual, some other variety x, maybe check. And each of them has these two Q difference connections, and the Q difference connection in the variable z from one is the curve counting variable become a covariant. The covariant becomes curve counting, and that's one of the many. This is one of the many aspects that this 3D mirror symmetry does. And maybe to have something concrete in mind, you can ask, you can look at the kind of the simplest.
So
Interesting. Let me see here. Let's see, where Okay, let's continue for a moment and then we'll see. So so there's there is maybe the mother of all powerful Q special functions, or the mother of all linear difference equation is the equation satisfied by the hypergeometric function, and the mother of all certainly that the hypergeometric function specializes to all functions that we had on with the Airy, Whittaker, and so on and so forth. So so that's the similarly, there is a Q hypergeometric function, and in some sense is the mother of all kind of classical special functions that solve linear equations and that is the function explicitly given. So if you remember what was the series for the hypergeometric function, the Q hypergeometric function is the same kind of series, except you replace factorials by Q factorials, and the Q factorials, since we already discussed what's a Q gamma function, we know what's a Q factorial. It just means it instead of multiplying successive shifts, successive additive shifts of some variable, we multiply one minus multiplicative shift of some variable with denominator Q, and so that's the series, and that classically corresponds to classically it's known to solve a Q difference equation of order 2 in all variables. It's called the contiguity relations. And in particular, there is some particular combination of A that solves exactly the same equation that it does in Z. And so in particular, there's some combination of A's that exactly mirror the to Z.
And so Q is the same for your X and for mirror dual.
Yes.
Okay.
Because Q just comes from the domain. The mirror duals they live in the target, and the Q is a variable that's in the domain. Yeah. So yeah, and in geometrically this properly specialized. So you have to get rid of one of the A's. You can discuss separately how to get all three of the A's back. But then if you get rid of one of the A's, you specialize it properly. When you'll be in the situation of corresponds to T star P1. And T star P1 is really the mother of all, well, the mother, progenitor of all possible subplatonic resolutions, and that's so maybe I'll explain definition of subplatonic resolution in this slide. So it's first of all, it's a resolution singularity. Means it's a smooth algebraic variety that maps properly and birational to affine algebraic variety. So in this case, if I take T star P1, that is the blow up of a quadric cone. And the quadric cone, I can think of, for instance, I can think of this as the set of nilpotent element in the SL2, and the nilpotent cones another Lie algebra. This similarly resolves by T star of their G mod, by the T stars of the corresponding flag varieties. And so this is a resolution singularities. It is symplectic, so visibly here, because it's T star of something, and it's equivariant, or people will sometimes say conical, in that there's an action of automorphism to the whole picture that in fact contracts the singular guy to a point. So if you have a nilpotent cone, if you just take a nilpotent matrix and you scale, it's still nilpotent, so it's a cone. So there's an automorphism that contracts everything to a point, and that's the third part definition of occurrence of subplatonic resolution. And as I said, this is really kind of the unicellular organism in the world of subplatonic resolution. So you should think of, if you think of the usual Lie algebras, Lie groups Lie algebras, there's some structure theory to them, and that structure theory says that in the end everything is reduced to SL2. So similarly, there should be, we're we have some pieces of that, but we don't have the complete theory yet, I guess. And we don't have really the definition. I don't think this kind of occurrence partial resolution, I don't think it's the final definition. But when there is a definition and there's a theory, structural theory, then we will see that in the end all of them reduce to P1 by some operations, which maybe we're not going to discuss today, but there's some operations which now come in two dual flavors corresponding to for ordinary Lie algebra. You have to look very carefully to distinguish roots and coroots, because the kind of what exchanges roots and coroots is well, okay, you have to be kind of trained in Lie theory to distinguish them. But for this sort of things, there's dual notions of roots and coroots, which are really two completely distinct things. And so correspondingly, you can break up your variety in two different ways. So you can, when you're going to reduce, eventually when you reduce it to T star P1, that this can be there are kind of two ways to break up your variety, and eventually going to get T star P1.
And here what you have is a Springer resolution of the nilpotent cone. Am I correct?
Say again?
Is this the Springer resolution of the nilpotent cone?
Yeah, Springer resolution of nilpotent cone is an example of symplectic resolution. Yes, that's what I'm trying to say.
I see. And this one seems to be the same, right, in this example here. So there's a general notion of symplectic resolution. Maybe I'll repeat the definition. It's a symplectic manifold that maps properly and birational to a fine manifold, which is such that there is a group of automorphism that contracts the fine manifold to a point. An example of that is a Springer resolution. An example of Springer resolution is this resolution. For SL2, this is this resolution I'm talking about. Okay, thanks.
Sure. Anytime. Other questions? Right. So if I look at the kind of general tree of life of symplectic resolutions, there's some there's some variety there. So there's kind of AGE type of organisms, and and there's most interesting one geometrical. There are sheaves on surfaces. So moduli. So if your surface is symplectic resolution, then moduli sheaves of surfaces are also symplectic resolutions. And so this includes these are the AGE surfaces, and this is geometrical, maybe the most interesting ones. And this is and that's very nicely illustrated by the Van Gogh picture, which exactly has sheaves, and the first sheaves sit on the surface. That's pretty clear here. But I think, so like I said at the beginning, I think this is a very nice definition of symplectic resolution, but I don't think it's the absolutely the right one, because I think you have to somehow include some other varieties which may not be resolved, or sometimes when you have a resolution, maybe it's not good enough. And so this is there's some technical issues I want to go into that, but eventually we want to talk about some kind of modular vacuum, some kind of physical theories, which I'm intentionally being super vague. And so it's this come in a few different flavors. And so I would like to have a unifying mathematical definition for all the objects I want to consider, but maybe this is not the subject of this talk. For the subject of this talk, maybe we'll stick to this symplectic resolutions as I discussed them.
But it's not generalization of only simply laced part of the 20th century. You mean you have geometrically, you cover not only ADE, but like BC?
So here it's you have to distinguish a little bit between whether there are like ADE quiver varieties, which is not the same in general as so what I meant here is this kind of ADE type quiver varieties. But you also there are other series. There's also the classical one, the T star G mod P. It's another example. There's also other series. And so there's by way of symplectic resolution, there's some infinite series in which the largest one are the quiver varieties, and inside of quiver varieties, the geometrically most interesting
subset are the sheaves on surfaces, but then of course there's plenty more. So that's well, maybe I'll stress one more time that I love the definition of symplectic covariant solutions. It's wonderful, this marvelous definition. I don't think it's the final one. So I think this is the maybe it's okay to say it's a Lie algebra of the 24th century, but maybe you shouldn't be thinking. You should be thinking a little more broadly in the 21st century also. Okay. So maybe I'll be completely honest with you. This is, you have a singular variety, and in some smooth varieties we can't really set up the K-theoretic equivalent count quite correctly. So the Nakajima variety is the best possible situation when we are the nice varieties, there are nice simplex resolutions, there we can set up the K-theoretic counts super well in them, and so that's the poster boy of this whole world. Yeah, but there are also situations where even if you have a smooth resolution, you may not be able to set up the count correctly. So that's all right. So this is I was as I was saying before, you have an interpretation of some linear differential, some difference equation as some quantum differential or quantum difference equation, and that gives you this interpretation is valuable because it gives you a precise geometric interpretation of a whole bunch of things, and maybe one of them is elementary. And I'll start with that because you can. This is something even if you don't care about. Even if you don't care about the enumerative geometry or anything like that, maybe you can appreciate like a basic analytic point about it. And then so this is something we call pole subtraction matrices, and then I'll talk about, so you have an equation in two kinds of variables, the monodromies and both equivalent and scalar variables, and then we'll talk about how it's actually determined. Computed means formulas, and I'll talk about categorification monodromy, and then tomorrow will come, so we'll see. So one more general thing I want to say is that this is more of again, if you lost, I hope you aren't, but if you are, maybe you can take away the following point, which is I find very important. I kind of find it important for myself, is that the monodromy, you should think of this as monodromy is something that tells you how to trade a solution written in the neighborhood of one point. Let's say you have a solution in Z, and then you're trading a solution written in the neighborhood of Z equals 0 to a solution written in the neighborhood of Z equals infinity. Well, you should think about the monodromy is kind of like an interface. You have we were talking about maps from P1 to some target. And now imagine your target. So the summation when we're summing over curves of all possible degree with Z to the exponent depending on the homology class of the curve. This is you can think of this as a curve being weighted by a factor that depends on its area, because if you pick if you use the area form, that the area would be proportional to homology. So you should think of this as now imagine you have a situation where that area form goes from being a Kähler class on one birational model of X to Kähler class on another birational. If X undergoes a flop, and in the middle there's a singular variety, and that is, as opposed to being somehow happening abstractly somewhere in the world of ideas, it's actually going to happen up concretely over our world sheet. So we're mapping to P1, but our target is we're mapping from P1 to some target X, but that target X is changing depending on from which point of P1 we're mapping. And so then you get something associated with X at one part of your P1 and something associated to the flop of X at some other part of your P1. and then the interface between them is what analytically continues from small z to large z. So that interface you should imagine there's some kind of actual physical interface. But mathematical we study as whatever, some how are you going to think about interfaces? Either maybe eventually you want to categorify it, but you can also think about it as a correspondence between different things, correspondence between x and the singular and in the flop, and where I'm driving with that is that in particular that point of view very clearly explains why the formulas of monodromy always factor in the product of say two things. So like if you wanna write a formal monodromy is maybe in the simplest possible case of Knizhnik-Zamolodchikov equation, then the monodromy of along one simple loop is just the R-matrix. And the R-matrix you write as two things kind of crossing, like I wrote here. But you should think of this as a product of two operators. One is when they come together and then they come apart. First you go from non-singular to singular, and then from singular to another non-singular. And so then this is the type of formulas you get in geometric, the kind of geometric theory of quantum groups that I'm discussing here. They always of this form. Your monodromy is factors of two operators, kind of one operator and the inverse of the other operator. And then that makes any sense?
Yeah, actually, I mean, just it's similar picture for the 2D mirror symmetry when you go from one cusp in the Kähler moduli space to the other one. And so that's you said something about categorification. There was this very old, I don't remember, I think Kontsevich was the first, the action on, if you replace all these by derived categories, it will be action of pi1.
Yeah, exactly. So if you can scroll ahead in my transparency to that part. Yeah, that's coming up. Yeah, so this is
all right. Okay.
Right. So all I'm saying is that you should think of the monodromy. The way to think about monodromy is to be a product of two things. When if you wanna go from 0 to infinity, you have to go through intermediate thing, and that intermediate thing is some richer theory. You go to some, despite the fact that I draw it some single variety here, at an intermediate point there's some kind of richer theory. You go inside the richer theory, and then you come outside of on the other hand. And that's this is why your matrices will all be a product of two things. You kind of go into a bigger world, and then you come back on the other side. So that's the, and I think for the on the outside chance you want to learn more about this particular point of view, I've been teaching a course about it, of which now there are 20 installments available on the web. And so I don't know if you want to start, and I haven't have not yet concluded. I don't know if I want to start listening to 20 plus.
So and the links are on your homepage. It's just for graduate students.
It's if you look at my seminar page. Well, anyway, it's on my seminar page. Yeah, there's a link. Yeah, you can use this anyway. But that's slightly endless right now. The course, I'm not saying you should do it, but if you're anyway. So let's go back to that pole subtraction. This will be completely concrete discussion. So this is if you lost in some categorical, whatever, some higher stuff. This is complete. This is elementary. This is elementary math. And so suppose I have an equation in two sets of variables, like I had for Q hypergeometric functions. I had so I have two kinds of variables, and I said that each one of them the equation is regular. But in fact, the kind of basic point is that it's not going to be regular jointly, which means that if I send one variable to 0, the solution grows at most polynomial. If I send another variable to 0, the solution goes most polynomial. But if I send both of them to 0, then the solution in fact grows super polynomial. And then the other way to see it is that there's if I take a small neighborhood of 0, small partial neighborhood of 0 in both groups of variables, there will be no holomorphic solutions to my Q-difference equation holomorphic in that domain. And that's a simple thing, but since This is for Q difference. This is for differential equation can never happen. There's a general theorem of Deligne, pretty marvelous theorem, very deep and difficult to prove. That if I have a differential equation, that it's enough to check, and I want to know whether it's regular or not. It's enough to check it this near generic point of every component of divisor of singularities. Means here, if every singularity is like z equals 0 and a equals 0, it's enough to check that my equation is regular at one and regular in the other, and then will be regular jointly. But for Q difference equation, that's not the case, and this is a kind of absolutely elementary example. Is look at this. This is a silly example, but it already illustrates the point. If I take a 1-by-1 system, and this is with this, if I shift Q, I get A, and if I shift A, I get Z. So if I shift by Q Z, I get A, and if I shift A, I get Z. Okay, it's a system, and that has this solution, this exponential. I'll circle here. That kind of exponential is the solution. And what do we see from this exponential? That if my Z by itself goes to 0, then grows polynomially. If A by itself goes to 0, it grows polynomially. But if they both choose to go to 0, then it grows superpolynomial. And that's similarly told. So the singularity divisor here is a union of 4 P1s, and this happens, and there's 4 corners, and this happens at every of these 4 corners. And of course, this is a silly example, but if you want a non-silly example, you can take the 2-by-2 hypergeometric equation. That will have, as I said, this will have, there's some combination of A in which it's regular, and then there's a Z, and this will be not regular jointly. And so, well, you think it's bad, but in fact it's a feature. It's not a bug, because this means in the neighborhood of my one given point, I have in fact two different series of two different solutions. One is a series in Z with coefficient rational function on A. So it means it's something which is in Z, means in Z it's holomorphic, but in A its poles accumulate to the origin. And then there is, so this is a picture to go. So if I have a Z solution, which is I think in this picture drawn in blue, then in Z it's holomorphic in some neighborhood of the origin, but in A it has poles that go accumulate to the origin, because if I go deeper and deeper in my coefficient Rn of A, then I get more and more poles, so I get things which are accumulate to the origin. And then there's the other kind of solution, and so it means I have two kinds of solution of the same system of equations. It means they're related by, if I take the ratio, means there'll be an elliptic transformation matrix that takes one to another. We call it pole subtraction matrix. And so this is, maybe again I'll say, this is not usually studied in the world. I mean, this is a little bit like Stokes phenomenon, but it's a little bit different from Stokes phenomenon. Anyway, it should be maybe in some aspects it's as powerful as consideration of Stokes data. In some aspects it's maybe kind of more elementary than consideration of Stokes data. And maybe I want to compare and contrast the two things. So if I take the so what's the monodromy? Monodromy, when you take a solution at one point, say Z equals 0, and you compare the solution to some other point, maybe Z equals infinity. And so then the ratio would be a meromorphic function, which is elliptic function of Z. And then and the pole subtraction matrix, that's just the ratio of two kinds of solutions at the same point. And so this is, we're going to compare and contrast them, and then they're both elliptic. However, then the properties is different. To compute the monodromy, it's really an analytic. It's really an analytic question, whereas this pole subtraction is really algorithmic question, because it really is about find some elliptic function with. So what you need to know is you have to trade poles in one variable for poles in another variable. And so if you want to eliminate poles in some solution, all you have to find is an elliptic function with some given elliptic function with some given singularity. That's all you're doing, because that's an algorithmic problem. So that's you don't need to sum up any infinite series to do that.
And the third point is that this matrix, this pole subtraction matrix, that constrains monodromy via the following commutative diagram is that if I'm interested in the monodromy, so maybe if I'm interested in the kind of this fixation, I'm interested in the monodromy. Instead, I can compute the monodromy if I know the pole subtraction matrices. Instead, I can compute the monodromy for when A equals 0, because I can trade the series in the neighborhood of z equals 0 for just expansion as about A goes to 0. And then in that expansion, this would be all that happens. All I care about is the initial term of that expansion, and so then it means I compute. If I know that pole subtraction matrices and I know the monodromy at A equals 0, it usually means some kind of triviality, because it's usually A equals 0 means you have to kill some variable in some equation. So that means usually either trivial or much simpler equation, and then that tells you the monodromy has this kind of thing, right? So this is maybe that's another reason why you should think of monodromy as going to factor, because here it says, well, this is some matrix, and then in fact this matrix is triangular, the first vertical line. So you start. What would be a good colors to use? This color. You start here. That's one kind of triangular matrix, and some matrix which you think maybe it's like a diagonal matrix, and you come back here. That's another triangular matrix. The triangular the other way. And so, okay. And so in the geometric constants, for instance, the two sides, the kind of extreme sides, the simplifications you find are the following. So if my variable is the curve counting variable, then if I kill that variable, there's just no curves, and so that means I'm back to I'm not counting any curves. I've set that variable to 0. Means all terms of positive degree are gone, and I'm just doing old computation in K-theory. So that's easy. And if I set the covariant variable to 0, that's the same as doing the quantum difference equation for the fixed locus of the corresponding torus action.
So, not for particular A, but sort of A capital for the torus.
No, it just means, so what does it mean? I have some variable going to 0. It means I have some set of variables, and that corresponds to some subtorus. You think of the computification of the whole torus as some kind of toric variety, and setting various parts of my equivalent variables to 0 corresponds to going to different strata of that toric variety. So you can have a kind of, if the deeper you go, the more the fixed points of the bigger torus you're going to have, and so in particular you can take the whole torus. The whole torus will be an example of that. So okay, usually that's typically simplified. Like for example, the fixed locus very often could be zero-dimensional. If x is zero-dimensional, it's not true that maybe slightly surprising fact that the computation, if you set properly the computation in case of zero-dimensional variety, it's not stupid, but it is simple. Because it's listed one-by-one Q-difference equation. One-by-one Q-difference equation, okay, we can master.
Yeah.
But
I meant that if you take the kind of the smaller subset of A's, your fixed point set can be, I don't know, non-compact or some very bad, in the sense that if you have the bigger torus you have, the more chances that you have your zero-dimensional or fixed points locus.
Right, we don't really need here anything to be compact, because yeah, right. I mean, there's in the abstract development of the theory, it's good to be able to take fixed points with respect to arbitrary subtorus. But you're right, for concrete computations, if you have an action, you take that fixed point. Yeah, that's right. But maybe point about compactness from the definition, our axis of the form projective over affine, so we don't really need compactness. Means all fixed points will also have the same property, so it's going to be projective over affine. Means all the kind of curve counts are well defined without we don't need any sort of proberness assumption further than that, because any curve will be contracted to a map to a point by the map to affine, and so curves can only move which is in projective varieties. So and so the first point I want to make that in fact this kind of pole subtraction methods are geometric. They come from a certain correspondence. So you see we want some correspondence between the fixed locus and the variety x, and this correspondence, since it has to be an elliptic matrix, has to be correspondence in equivalent elliptic homology. And the reason that this is kind of natural for this to be geometric is because well, I think equivariant computation is the world's best tool for proving that poles in some formulas cancel, because the typical situation. Let's see. So a typical situation. So very, very typical situation in algebraic geometry or whatever enumerative geometry, that you computing something by localization, and then it gives you something which has poles, but when from algebraic geometry, from geometry, you know it's not going to have poles. Right, so that means there's some geometric things for pole cancellation. And I saw Lisa Jeffrey at some point at this call. I don't see her. She of course knows all about that. And many other people in this audience know about all of that. So this is super classical in some parts of math. That the equivariant computation is an amazing way to prove that the poles cancel. And maybe if you haven't seen this before, you can think of the wild character formula, which amounts to tracing over sections of a line bundle over G mod B, and if you compute it by localization, you get this formula which has denominators. But from either representation theory or symmetric function argument or geometry, we know that this denominator is going to cancel because I mean we're integrating we're taking Euler-Kirchhoff coherent sheaf on the projective variety, and so that is okay. So that's this is what I'm saying is that in the problem, and maybe another kind of recent example, not directly related to the subject of the talk, but another example, which is where sort of thing which was recently used very much in this Nekrasov theory of QQ characters, where you phrase like a difference analog of the Virasoro constraints as some absence of some singularities, and you use again equivariant consideration to prove that in fact there's no singularity. So
I think compactness is important in his story, and he spent some time.
Yeah, absolutely, yeah. So this is I'm also saying here for us compactness is somehow that is the compactness we need is provided automatically here. So that's the right. And so what's that correspondence? I don't want to peddle about this too much. So it's like at every single talks I give, I have to somehow say a word or two about this elliptic stable envelopes. The correspondence is an improvement of some very natural correspondence. If we have a fixed locus and you have the ambient variety, then there is a very nice Lagrangian correspondence that takes that's just attracting. So not only you have a fixed locus, but also you have the direction. You say A goes to 0 as opposed to A goes to infinity. That also tells you this tells you a certain direction in which how am I supposed to approach that fixed locus. And so then you give this attracting manifold, which in our situation it's a symplectic. We were started with symplectic manifold. Attracting manifold will be in general Lagrangian correspondence. And then there's some kind of yoga, but except that this correspondence is not proper. So again, to Jan's point, properness is important. That correspondence is not proper, and so there's some kind of yoga about how you extend this to a proper correspondence. Is how do you extend this attracting manifold over different strata of your variety? And that's originally we've developed that kind of theory in cohomology with Davish a long time ago. But in the elliptic cohomology is what we need here. This is something we do with Mina. And maybe I should maybe if you're to relate to something to some people think about that sort of thing.
is like suppose if I go back to moduli of sheaf type interpretation, then the attracting, so if in the moduli of sheaf type interpretation, the fixed locus is often interpreted as the locus of direct sums, and then the attracting manifold is the locus of extensions. And, somehow a lot of people love and use locus of extensions as a good correspondence for many good purposes, but that locus for the purposes that we need here has to be made proper over, it has to be a proper over X. So you have to complete it in some canonical way, and that's one of the many things that the stable envelopes do. So there's certain completion,
which makes it singular, probably. Yeah? It's like I'm thinking by analogy with 20th century that you have Schubert cell and you go to the closure, and so adding some smaller dimensions, so you have Schubert variety, which is not smooth, and so then you don't. I mean, it creates some problem which people in 20th century.
You solve problems, and so maybe since Jan brought it up, maybe I'll make this point. Is that so? Take a Schubert variety, take the closure of a Schubert variety, and so or in our situation, more since we're talking about more symplectic things, take the closure of conormal to the Schubert variety. But of course, if one is strictly more complicated than the other. So closure of conormal, it contains, if you look at the zero conormal vector field, that will be the closure of your Schubert variety. So, okay, people were trying to define the class of that singular variety in elliptic homology, and they noted that it cannot be defined because it depends on, if you push it forward from resolution, then the class elliptic homology depends on which resolution you choose. However, this theory bypasses this beautifully. It gives you a canonical extension, the canonical elliptic correspondence, which is the so to speak, is the right thing to consider. That contains.
What do you mean? That there is canonically defined kind of maximal or whatever extension?
No. It's like this. So this is you should think. So what is a class in elliptic homology? A class in elliptic. Well, what's like a K-theory class or a homology class? It's like, what's a K-theory class? A K-theory class is an element of a ring. So it's a section of O on the corresponding scheme. Okay. In elliptic homology, we don't have the ring, we just have the scheme. And so it's a section of a line bundle. And then you have to say, well, in elliptic homology, the line bundle is going to depend, we have some moduli of line bundles, so might as well have moduli of this set. We have some moduli of line bundles. Like, for example, we have some peak 0. And we might as well, if you have a peak 0, we should be able to ask, well, how about we ask for sections of all those different line bundles, and that is what elliptic stable envelope is. It's a section of all of them, so it contains all possible resolutions in particular, but it's some analytic option. It depends on this. It depends on continuous variable in some peak 0, and that's. And if you somehow specialize them appropriately, you're gonna find all the things that people were trying to consider fine before. Anyway, and it has to be here too, because here it has to contain the Z dependence, and the Z dependence has to depend on Z. Z is a variable in peak 0 of your elliptic homology, or peak of which comes from peak on your variety, in fact. So and so there's a theorem which we proved back then with Mina, is that pole subtraction matrix is that elliptic stable envelope. So we have to so again to reinterpret the what we're trying to accomplish. We're looking for some correspondence between the fixed locus and the M variety that cancels poles in solution of the quantum difference equation in a certain precise way. And that correspondence is the elliptic stable envelope. And the variable z, which counts curve in one situation, becomes a variable that parameterizes, that tells you of which line bundle this is a section on the elliptic homology. Okay, that's one theorem. And that elliptic stable envelope is a half of the geometric R-matrix. And in particular, this is as a corollary, we get the following result that you know, what if we want to compute the monodromy in the current variable. So we already I stressed a bunch of times that if you have that the monodromy is going to be a product of two things, and here the product of the things we start with a equals 0. We do the pole subtraction, go to z equals 0. At z equals 0, we have no curves. There's somehow nothing to. That means a very, very simple equation. There'll be some diagonal matrix corresponding there, and then again we get another stable envelope, which is now corresponds to a goes to infinity. So this means what does it mean? We change from a going to 0 to a to infinity. It means we interchange the role of attracting and repelling sets, and so you get the stable envelope for the elliptic stable for one kind of attracting correspondence, and then you take the same for the repelling correspondence, and you take the ratio, and that is the R matrix. That's the general elliptic R matrix, which is in somehow. In fact, for many instances, is this is in that generality. That's the elliptic solution of Yang-Baxter equation that's constructed by Min and the way to relate it to R matrices more directly is that maybe to some visually related to some R matrices that you know more familiar with is that if you take if you think about what does it mean a goes to 0, a goes to infinity, it means in general a goes to different strata in some toric quantification of your torus, and these different strata are, if you think of the toric quantification in terms of a fan, this means you go to you know, here's a picture. Here I draw a picture of a fan, and so that's this means you go from one cone of a fan to another cone of a fan, and that's exactly what R matrices do. So that's the picture. So to summarize, this proves that this pole subtraction theorem proves by the argument I explained here, that proves that the monodromy of the equations in the current variables is the elliptic given by elliptic R matrices. In particular, in many instances, the equations in the current variables are known to be the QKZ equations, and so this proves, which is in full generality was not known, that the monodromy of QKZ equations is given by elliptic R matrices. So that's you know kind of one basic result that is recovered and generalized in this situation. And then as I said before, there's a 3D mirror symmetry that exchanges the equivalent variables and the scalar variables. And so then you can ask, what about the similar setup? What would be the mirror setup and the scalar variables? And the mirror setup and the scalar variables would be an example of that is the following setup. This is should remind you of the picture you've seen on one of the slides before, is that I can have some quotient stack of the form a fine algebraic variety modular reductive group. And then for different choices of stability condition, I have two different stable loci. And then correspondingly, I have two different points in the toric compactification of my Kähler torus that correspond to this two stability condition, and I can ask about the monodromy of the equation in Z from the one point to another. Phrase it differently, instead of now a cone corresponding fans corresponding to different possibilities for tracking repelling directions for the action of a group, I now have same picture, but now for the action of the group by which I mod out is the group G. And so I have all these fans describe different ample cones of different quotients, and I can ask these fans correspond to different different infinities at the compactification of the Kähler cone, and I can ask about the monodromy from one to another. And so then there's a completely analogous theorem that this is again given by exact same formula. So you get the stable and the inverse of the other stable, and this again you can phrase in the way you can phrase this extension. One way to phrase it is that suppose you have an open set and you're trying to extend. So this is stable only with a certain canonical extension of elliptic homology classes on the stable locus to elliptic homology classes on the whole stack. And then how you should think about it? If you have an open set inside, so your stable locus is some open set inside the stack, and then this usually means that for cohomology of that open set would be a closed subset of the cohomology of the stack, and so that usually happens. So this means you have the cohomology of the stable locus is some embeds in the cohomology of the stack, and that's a closed embedding. And then you can ask, then you're asking about interpolation. What does it mean to extend a class? You're asking for a section of some line bundle that takes given values at given points. So that is to say, that's an interpolation problem. And then you can show that abstractly that the interpolation problem has a unique solution. That's the stable envelope. That's one way to phrase what stable envelope is. And so once you do that, then you can do the opposite operation for the other stable locus, and then you get a matrix with tick matrix, and that's the monodromy in the z variables. And I should remark that this is not only computes the monodromy, but also gives you kind of a, in fact, you can think of this as an integral formula for solutions too, if you want. Okay. And so now we come to categorification, and this is in the situation with quantum differential equations of the Braiding connection. At the dawn of the subject, Maxim Kontsevich said that that the monodromy, if you take the monodromy of the de Broglie connection, that should in fact lift. So you should not think of the connection is on a trivial bundle with fiber decohomology. Well, not a trivial bundle, or the fiber of your bundle is cohomology of your variety. And instead of asking for automorphisms of the cohomology, in fact, you should be thinking about automorphism of the whole drive. And there's been work on this. People like Horia and Borisov, they shown that this is the case, for example, for toric varieties. Yeah, you want me to say more, or people somehow?
No. I think that's it depends. What will you say next? So what's in your next slide?
And so this in this spirit, there is a theorem of Bezrukhavnikov and I about categorification, which says that this is in fact it's for strictly speaking for infinite series of symplectic resolutions, and for known infinite series of symplectic resolution, that is true, and in fact true with the identification of intermediate categories. So this is again of the same in the same spirit as I'm. So the kind of I'm trying to frame my message always in the same mold. Instead of going all the way, I want to go halfway and halfway. So I want to find something that goes, something goes halfway, and then something, and the same kind of thing that goes maybe right. Right. My monodromy is a product of two kind of things, one and the inverse of the same kind of object. And here the intermediate categories are the categories of the quantizations of your variety X over a field of large prime characteristics. And that's a subject. In fact, when Kaledin and other people thought about this kind of axiomatics and structure of symplectic resolutions, they weren't so interested in curve counting, but they were interested in quantization a lot. And so this is there's been a lot of work by Kalejian, Bezrukovnik, and others about quantization of symplectic resolution. And in particular, if you quantize them in prime characteristic, you get interesting. So if you quantize them in zero characteristic, that's an interesting thing. But if you quantize them in a prime characteristic, you get derived equivalences with your original variety. So you get the categories of modules of quantization that that is derived equivalent to sheaves on your original variety. So then we can go, this kind of monodromy again is going to factor into two things. So this will be, first we go to modules over quantization, then we go to the flow. And so maybe before I go to an example, I want to point out that this is the way you should interpret this is not through what in this picture we know and what in this picture we don't know. And truth is the information, there's some information that flows both ways. There's some stuff which is obvious about quantization, which is not so obvious for quantitative varieties, and vice versa. And similarly, there's some things which are obvious from kind of differential equation point of view and not so obvious. So there's a flow of information in all directions. But one point is that what's the role of monodromy in the group? The role of the monodromy group in this case is just really replacement. If this sort of thing specializes to Kazhdan-Lustig theory and characteristic P, and then Kazhdan-Lustig theory and characteristic P, the main role is played by, in large characteristic P, the main role is played by a affine Hecke algebra of the same type, and the monodromy group is a generalization of that affine Hecke algebra. So that's everybody knows that Hecke algebra is the monodromy of some, or affine Hecke algebra is the monodromy of some particular nice differential equation, and that's the generalization of that statement. And so an example of that, let's think of like the Hilbert scheme of points in the plane. This is the first kind of modular shape type example in that I want to talk. Have about. Well, this corresponds to Nakajima quiver variety. So maybe it's your variety like that, and the dimension vector is this is n and this is 1. And so then the singularities of the quantum differential equation are the roots of unity of order at most n. And here I try to draw them for n equals 5. And then my solution, I'd like to think of this in terms of two regions. One is when z is less than absolute value than 1, so the interior of the unit disk, exterior of the unit disk, and in different parts of the unit disk between different singularities. And so then it's inside the unit disk, my series, that Hypergeometric series converges, and so this is what corresponds to the Hilbert scheme of points. Outside, that's the theory for the slope, and in the middle, I have this also intermediate segments that correspond to modules over the quantization, and the correspondence to the modules of the quantization of the Hilbert scheme of points. This is these are the same as modules. The actual quantizations are the spherical subalgebras and Chernyshnik algebras, but that's a Morita equivalent to Chernyshnik algebra itself. So you're talking about Chernyshnik algebra, size AN, or whatever, JLN Chernyshnik algebra, sorry. And then Chernyshnik algebra has a parameter. That's parameter over quantization, abstractly corresponds to a peak of your variety, and that parameter has to be of the order log z over 2 pi times p here. So maybe more general, if you think of what's a multidimensional generalization of this picture, is that you're going to go, the analog of the unit circle here is the compact torus inside your Kähler torus. And then if you take the log over 2 pi, that goes to the Picard lattice of your pk tensor R. And we've also scaled it by p, and these are the pk tensor R. This is where the parameters of quantization lie. And there are hyperplanes that correspond to certain. These are the roots, if you want, of one kind of root. If you're a variety, the hyperplanes correspond on one side to the singularities of the equation, on the other side to bad parameters of the quantizations, and the complements correspond to this orange region. So this is the kind of good parameters of quantization, and then Bezrukalnikov and Kaledin construct the sort of equivalence when you go from commutative to non-commutative, and then you can use the same thing from non-commutative to the flop. And so that's the theorem is that actually that is the this map is a categorification of the monodromy. All right, and so I guess I'm almost done. And the main ingredient of the proof is again has to do with stable envelopes, and it has to do with showing that under this Bezrukalnikov Kaledin equivalence, the stable envelope corresponds to the parabolic induction. That's in abstract situation takes some. In concrete situation that's easy to prove, but in abstract situation takes some argument to prove this. And now we come to tomorrow part. Is that well, you can ask why do we have this large prime characteristic? And the answer is, this is really an artifact. You should, if you're asking for really underlying reason why something like this is true, that instead of thinking of quantization of x at a large prime characteristic, this is like standing representation of Lie algebra in large prime characteristic. But instead, you should be doing that is the same theory as doing with quantum groups of roots of unity. But now, quantum groups of roots of unity, then the distinction between large characteristic and the small characteristic is not so dramatic as this for Lie algebras. And so it's much more natural to study, in fact, instead of studying modules over characterization, modules over quantizations of x and large prime characteristic, it's better to study modules over kind of quantum group type of quantization of x at a parameter of your deformation being a root of unity. And and then the link between that quantization and the enumerative geometry is much more direct, in fact. So this is underlined by the fact that this is a theory which is in some sense, well, I guess it's simpler than prime characteristic, but it's also more well behaved than prime characteristic. So that's much more. And maybe the reference for this, you can watch old video of a talk I gave at the Clay Math Institute 20th anniversary and how that's supposed to work. But that's there's some outlines of how that's supposed to work, but that's put meat to that bones remains to be done tomorrow. Also, another direction in which it's very natural to go, but that somehow again that's been postponed till tomorrow, or maybe somehow that hasn't been done yet, is that instead of thinking if you're thinking how you want to, so this is how you're going to categorify elliptic stable envelopes. And so you think, well, elliptic homology, where is it supposed to come from categorically? Well, of course, it's going to come from loops to x. And so then what you should really be doing is quantize not just x, but also loops to x. And this would be some Q-vertex algebras, and then this all the correspondences we do, all the correspondences within this paper with Roma, they have to do, so it's maybe roll back here. Yeah, so this is the this is stable envelope in K here. And if you want something like this in elliptic homology, or you want to categorify any other aspect of elliptic homology, then what you should do, you should look at loops at x. And again, there's some outlines how that's supposed to happen. And this is, you can look at my talk at String Math, and that's. But again, this will be certainly I'm not going to report on it today, since I haven't even done it today. So this will be more like for tomorrow, to put all the technical details there. So, but that's so I think I'm at this point out of slides, and so maybe I'll take questions.
Yeah, thank you very much. By the way, on your previous slide, should we think about this quantization at the finite characteristic as the analog of this interface in your intuitive? You have some intuitive picture when you go from one cusp to another one, kind of when you describe the monodromy. Yeah, and now you replace both ends of this path by the derived category, but in the middle you had something which was sort of a degenerate, like degenerate cone.
Right, right. So this should be the that's right. So this is the maybe like that. That this is this you know, going from here to going from here to there, you should think of this map as kind of like the interface. Yeah. It's these are the categories. These are the categories you should be. So if you have some if you want to say complexified Kähler class, and then add the situation where your Kähler class itself is 0, but the complex part is not. The correct category there to put is this Bezrukavnikov category.
Which is non-commutative. It's not like DB on some singular story. It's conceptually non-commutative.
It's of course this is the I'm not saying it's well, maybe I should say that it's much more, if you do roots of unity, then it will be maybe much more geometrically there. But if you have different categories that are equivalent, of course it's a little hard to tell them which of them should be the geometrically one. I kind of like the roots of unity better, but that's the same for it means a fact for this sort of situation, that if you quantize in prime characteristic or you quantize to kind of quantum groups of roots of unity, the result would be the same category. If you compare a large prime with large prime root of unity, so that's which bright corresponding root of unity.
Okay, thank you. More questions?
I have one question about this transition between the flops. So there was one technique about using some window from the GIT theory, and you seem to also working in that direction to construct like a magic window to go from one dBco of 1x to the dBco of a flop. I wonder how that compare with this BK theory of using some quantization as an intermediate category. Is there a link between these two stories?
Oh yeah, that's the yeah. So whether this is probably the same or is I maybe I'm a little blanking right now, whether it's probably the same or it's I think it's more or less we can prove it's the same. Yeah.
Okay, thanks. Is there a reference like where one can read or the window?
Yeah, so this paper, this paper was so so there's this papers which are I don't know. So this is if you think about this Dan Nachel's and Sam's original paper,
yes.
they have some reference to some paper about like categorification staple envelopes that David Schmolik and Dave Nachel and I are supposed to write, and that's okay. That's been in some kind of draft for N years now, and similar to that paper with Bezrukavnikov is in some kind of draft since past 4 years or so. So so I apologize. I realize this is what's the word? This is not a responsible behavior to take such a long time to finish drafts, but I'm doing the best I can. What can I say? So
okay, thanks.
More questions? Yeah, I have kind of maybe a reference question, because there is this activity in Canada, but people like Ben Webster and other affiliated with him, and I mean, is it the same story or it's not? I mean, not about envelopes, but about when we talk about mirrors, just about the mirror symmetry part, this 3D. Yeah, I mean, I also remember some Bezrukavnikov Kaledin in his paper, and they defined some. You see, since you mentioned this Lie theory, they define some analog of the category O.
No, so this is the there's an old work by Webster. I mean, of course, so maybe I should say there are many people in the world who work on 3D mirror symmetry, and also a lot of people who work on quantization of symplectic resolution. There's a work by Webster and his collaborators, which is kind of important for work about quantization and characteristic zero. It is important, but it comes after the work of Kaledin and Bezrukavnikov in characteristic T, but contains maybe more details than Bezrukavnikov and Kaledin. So I'm not in that business. I'm not prepared to say who was first of which.
No. It's not about the priority. It's just whether it's in the same.
But in terms of having a clear, presumably eventually there will be some another specialism, but I think it's in characteristic P it's much easier to have a derived equivalence with to have the kind of equivalence we're doing here. It's much easier in characteristic P, because in characteristic P, how does a derived equivalence appear? It's you would just think about modules over. You take a module of quantization and you think about it as a module over the corresponding P center, and the corresponding P center is more or less your original variety. And so that's roughly how this works. Whereas in the characteristic zero, then you have to talk about maybe modules of subtraction, or maybe Hodge modules, or maybe some other structure. And so which I'm not. I mean, it's not part of my presentation today. I'm not prepared to talk about. So then, of course, Ben has a lot of other work about other aspects of 3D mirror symmetry. 3D mirror symmetry is a whole network of ideas, and you can somehow talk about them in different ways. The way I like to think about it is to actually have. So it's whether you have two things. You imagine them to be mirror symmetric, then I think in 3D mirror world you should be able to actually exhibit the corresponding somehow like the corresponding equivalence of the category of, say, boundary condition. You should be able to exhibit this explicitly as a kernel, but maybe not too explicitly, but actually have it. So this is the I think this should be easier than proof. So there are many derived equivalences in the world where it's possible to prove it exists, but it's difficult to exhibit the corresponding equivalence as some kernel in the product. But here I think it should be possible. With Mina, we have this general proposal, what this thing is like. We call this kind of duality interface, the mother class. We have a categorization in terms of elliptic envelopes, and so that's the angle I like. I like the explicit kernels. I like the at least it's the question of categorification. That's maybe a slightly separate question. But if you're content with just taking the K-theory class of that correspondence, which would be an elliptic homology class, that with me and I have this theory about what that's supposed to be, what that guy's supposed to be, and how it relates to Q-difference equation, and why it intertwines the Q-difference equation the way it's supposed to intertwine, and so on and so forth. But then, of course, there are a million other aspects you can pursue, and then, of course, I'm not pretending to be able to give any kind of overview of all this, broad spectrum of ideas.
Yeah, I have also some questions since you mentioned Nekrasov anyway. And also mentioned this example of a Hilbert scheme. So it's like C square, like symplectic surface and some category of sheaves on it. In Nekrasov's story, I mean, at least in his approach to generalization of instantons, he considered a collection of like symplectic surfaces, like coordinate planes or other whatever D2 branes in the Calabi-Yau in D6, which mean that it can be singular, like coordinate, like three coordinate planes in C cube. Either a 3D theory, I mean, either a version of this story which you explained today in this kind of a singular space-time or whatever.
So in principle, so in general, if you can ask for which kind of targets can we define curve counts, and in principle, it doesn't have to be smooth. It can be, maybe like a critical locus of some function, which is this could be studied. I don't think this kind of Nekrasov instanton counts on this singular surfaces in C4. I don't think it's an instance of anything that I don't think is an instance of anything I talked about here. You can try to relate them both to M theory or some such things, but as direct relations between the objects that appear here I don't see it. We're talking about the realm of this, or the things we do here are just various quantum field theories 2+1 dimensions, and that's the theory with a really extended superdistribution in 2+1 dimension. In terms of what the target could be, it could be whatever, whatever is there are many ways to describe it. Some moduli spaces of vacuum and some corresponding such theories. And then an example of that is the theory in maybe the main example of that is the theory on the stack of M2 branes and M theory. So therefore, it's also the theory on like a local curve in Donaldson-Thomas or Grom-Witten. Sorry, by I say Calabi-Yau, it doesn't have to be Calabi-Yau. There's no Calabi-Yau assumption here. I mean, Calabi-Yau assumption counts in 5-fold, but if you're talking about DT theories without any kind of Calabi-Yau assumption, that's also a theory on the local curve is an example of that. And then it is it's the fact that the Hilbert scheme is mirror dual to itself. It's the 3D mirror dual to itself. It is the fact that the corresponding DT theory on the local curve, that's just really DT theory on the local curve because your cross space is really C2. And then that corresponds to just really M theory on the curve with now being having not two but 4 transverse direction. And that's in this 4 transverse direction, there's a completely symmetric, and those transformations include 3D mirror symmetry and other symmetries for the DT theory of a local curve. But I don't see directly.
But your local curve has to be smooth. Like if you have a collection of coordinate planes, you have 3 D2 branes which kind of intersections.
Yeah, but it's also not. No, it's not. It's just. I think it's a different setup. This falls into some general category of like a sheaves on. Sheaves on Calabi-Yau force should sit inside some sort of M theory, and we're looking at some other corner of M theory, and so eventually they'll be connected, but not. I don't see a direct connection.
Okay. More questions? So it's a last chance to ask Andrei. Well, probably everything is clear, yeah, you know. All right. Well, thank you very much. So it's very inspiring talk. Very
yeah. Thanks so much. Thanks so much for everybody who listened to me. It's great to see a lot of old friends on the call and meet some old new people, and so